Hello and welcome. This is Columbia Basin Research's sixth video in a multi-part series on using Program SURPH. Program SURPH is a program created by Columbia Basin Research at the University of Washington School of Aquatic and Fishery Sciences. Program SURPH, Survival Under Proportional Hazards, was developed to analyze data from release-recapture studies of animal populations. In particular, to relate the survival estimates from release-recapture studies to individual-based and group-based covariates. Today in this sixth video, we will focus on analyzing some specific examples to show running through a paired release and the effect of timing of releases from a hatchery. A second example video, SURPH Lesson 7, will follow this one and demonstrate the relationships of migration distance to survival as well as length to survival. Alright, so let's fire up the program. Today, we will analyze sampling datasets, all from pit tag studies of salmonid smolts in the Columbia Basin River system to illustrate how to use SURPH to analyze release-recapture data. In this first example, we will be looking at joint detection survival modeling and hypothesis testing using the likelihood ratio test. The data for this example comes from the American Fisheries monograph by Burnham et al. 1987 and is a simulated paired release of pit tag salmon smolts in the Columbia River system. The data you'll need for this one is the Burnham dataset. The treatment population is assumed to be released directly into the turbine of a hydroelectric project. The control population is released directly into the tail race below the dam. The fish are then detected at 4 downstream hydroelectric projects, as shown here. The last site is also a detection site at which only the combined survival to detection at can be measured, which is required to allow estimates of survival to and detection at the previous sites. The assumption of a paired release study is that both the treatment and control mix downstream of the turbine passage experienced by the treatment fish, thus having common detection and survival probabilities. Burnham et al. 1987 recommends a series of models to use to test for downstream mixing, as shown here in this table. The hypothesis testing begins at the most downstream location and moves upstream. Though the tests are for specific site parameters, survival or detection, as each test moves upstream, the previous models that were not significantly different are set as common and used in the models. There are no covariate data, so only main effects are modeled in this example. Here, you can see the main effects dialog for detection survival and product parameters in their default settings for this example. This is the full parameterization and represents the alternate hypothesis for the model name H5S in the table. So we can double click on Create Model under Survival Modeling and name the model full. To create the model for the null hypothesis, click on the product main effects dialog. The caret on the navigation panel should now show it to be the active window as shown here. Now click on the common button on the effects control buttons, equating the product parameters as I've done here. Double clicking on Create Model, I can then name the model H5S. We can proceed creating the remaining models from the table. For the H4P model, ensure that the H5S model is active and change the detection main effects as I'm doing here. Create the model and name it H4P. Similarly, for the H4S model, ensure that the H4P model is active and set the survival main effects as shown here. Continue in similar fashion for all the models in the table. Here, we can see the detection main effects settings for model H3P. The settings for the final model, H0, should look as shown here. The navigation pane should now look like this. I can then double click on Estimate under Survival Modeling to create the results. To test the hypotheses, I can double click on LRT and AIC under Hypothesis Testing on the navigation panel and select Survival for the model type at the bottom of the dialog. The likelihood ratio test dialog appears as shown here. If I want to test the hypothesis H5S, I can simply click on the full result on the master model list and H5S on the testable model list. Corresponding likelihood ratio tests, LRT, statistics of 0.8437 is shown at the bottom, with 1 degree of freedom and a p-value of 0.3583, indicating that the H5S fits the data as well as the full model. Next, I can test H5S against H4P. Again, the result is insignificant with a p-value of 0.5969. I can continue the testing in a similar manner. In this example, all the tests have an insignificant p-value until we test H0 versus H1P, which has a significant p-value. This is what we would expect if there is a significant effect on mortality due to turbine passage. The insignificant p-value for the other likelihood ratio test shows that the two releases are mixing downstream. The parameter estimates can be examined by double-clicking on Parameter Report under View Results. Here you can see the parameter report for the final H1P model. Notice the large standard error for survival parameter number 3. If I double-click on Probability Report, I can obtain the resulting resulting probability estimates. Note the large standard errors for S1 and S2, and S3 is pegged at 1.0 with 0.0 variance. The evidence suggests that it may be possible to model the downstream survival with common detection and/or survival parameters downstream, and thus increase the resulting precision of the survival probabilities of interest. Setting the survival main effects as shown here, I can then create the model H1P common. Note that all survival probabilities share a common parameter except for the treatment survival through the turbine passage. After estimating the parameters, the likelihood ratio test comparing H1P common with H1P yields a p-value of 0.7594 as shown here, indicating that the new model fits the data as well as the model with the unique survival probabilities. Here we can see the probability estimates of the new model. Note the improved precision of the survival probabilities for survival in the first reach for both the treatment and control. Under the View Model Diagnostic Plots heading on the navigation panel, I can double-click on the Model Estimates versus CJS Estimates to bring up this plot. The CJS estimates are the best, albeit uninformative estimates of the parameters. If the selected model fits the data well, there should not be too much discrepancy between the two, and all points on the graph should lie near the 45-degree line. Although the capture estimates fit very well, survival estimates do not. Here we can see the residuals versus capture histories plot. If the model fits the data adequately, one should not observe any trends in the residuals, and 95% of them should be within the two red horizontal lines, plus or minus 1.96. Now let's look at the example of the effect of timing of releases from a hatchery. This example illustrates two-stage model development and hypothesis testing with group covariate data using analysis of deviance. A study of the effect on timing of release on in-river salmon smolts was conducted in the Columbia Basin River system in 1993. The data are given in the Dvorak dataset. You can see the input data file here. The group covariates middle and late are indicator variables, with 1 indicating that the group covariate applies to the population. The first 3 populations were released early in the season. Populations 4 through 6 were released in the middle of the season, and populations 7 through 9 late in the season. There is no group covariate for early release. This parameterization defines early release as the baseline survival. Note that the flexibility of SURPH3 would allow the modeling to be done without the use of the indicator group covariates. However, as noted in video 5, analysis of deviance is the preferred method of hypothesis testing with group covariates. Release timing can be considered a group covariate, so indicator group covariates are used to allow analysis of deviance to be used. Let's create 4 models encapsulating the 4 basic detection models. Number 1, population interval specific. Number 2, population specific. Number 3, interval specific. And number 4, common. First, open the detection main effects dialog and press the population interval specific button on the modeling effects controls buttons. I'll create the detection only model and name it full for full parameterization. Then I'll press the population specific button and create a detection only model named population specific. I will then do the same for the interval specific model and the common model. Once I've created all 4 models, I can double click on estimate under detection only modeling to estimate the parameters for all 4 models. The navigation panel should look like this. Next, I can double-click on LRT and AIC under Hypothesis Testing. Ensure the model type at the bottom of the dialog is set to Detection Only. When we click on the full model in the Master Model list and click on each model in the Testable Model list, the p-value is significant for each likelihood ratio test, indicating that the full model is the best model for the detection probabilities. However, we haven't yet taken into account the structure of the study design. The first 3 populations comprise the early release, populations 4 through 6 comprise the middle timed release, and the final 3 populations comprise the late release. If I double-click on the Manly PAR estimates under Data Diagnostics, I can bring up the closed form estimates of detection probability. These estimates suggest that there may be a difference in detection probabilities between the releases. If we can reduce the number of parameters for the detection probabilities, we can increase the precision of the survival estimate. I can set the detection main effects dialog as shown here and create the detection only model grouped. In this parameterization, we assume common detection probabilities within a release group, but unique detection probabilities across release groups, and then double-click on Estimate to estimate the parameters. Returning to the likelihood ratio test dialog, the new model should appear under the testable models list. When we test the full model against the group model, the p-value is not significant, indicating the group model fits the data as well as the full, and reduces the number of parameters from 18 to 6. This will increase the precision of the resulting survival probability estimates. We can now lock the detection parameterization and move on to the modeling the survival probabilities. Right-click on the Dvorak grouped result result and select Lock. The navigation panel should now look like this. The detection parameterization can no longer be changed without first unlocking the locked result. Here, you can see the Cormac-Jolly Sieber estimates after I double-clicked on Estimates under CJS Estimates in the data section of the navigation panel. As with all detection probabilities, there is evidence that there may be a difference in survival probabilities across release groups. We will look at the effect of release timing on survival using Analysis of Deviance. I can double-click on AnoDev under Hypothesis Testing. On the AnoDev Setup dialog, I press Continue to accept the default choice of Use Defaults. SURPH will then create the 3 basic AnoDev models as described in video 5, and the Analysis of Deviance dialog will appear. A p-value of 0.079 for the full covariate model indicates that the release timing is marginally significant. However, the full covariate model assumes that the covariate effect applies to both intervals. It may be the release timing primarily affects survival in the first interval. To test this, we need to create a model with this parameterization. Make sure that the underscore full covariate model is the active model and open up the group effects dialog for survival and set the parameterization for both covariates, middle and late. The ones in the interval 1 column indicate that the covariate is to be included for that interval. The zeros for interval 2 indicate that the interval 2 survival is not modeled as a function of the covariate. I can double click on Create Model under Survival Model and call the model interval 1. Now return to the Analysis of Deviance dialog. The Analysis of Deviance dialog should now appear. I can select the new model and press the down arrow to include it in the AnoDev model. The Analysis of Deviance dialog should now appear as so. The p-value is 0.04 for the line interval verse underscore grand mean, indicates that the model that included an effect for release timing in the first interval survival is a significantly better fit than the null model underscore grand mean. However, comparing the full covariate model with the interval 1 model produces an insignificant p-value of 0.329, indicating that the release timing does not have a significant effect on survival in the second reach. This has been lesson 6 on using Program SURPH, in which we analyze some specific examples to show running through a paired release and the effect of timing releases from Hatchery. A second example video, SURPH Lesson 7, will follow this one and demonstrate the relationships of migration distance to survival as well as length to survival. Please note that if for any reason you are having trouble with Program SURPH and these videos are not sufficient to answering your questions, you can find the user manual at cbr.washington.edu/analysis/apps/surph. PDF manual is there, and you can either load that in a browser as I'm doing right now, or you can download it to view in Adobe. If you're using Program SURPH and you have any questions or comments on that same page, you may also give us feedback via our user satisfaction survey. We greatly appreciate any feedback you have in helping us make future versions of this program to be more useful to our users. We hope that this video helps you get the most out of Program SURPH. Again, if you have any questions or comments in regard to Program SURPH, please fill out our survey as previously detailed. You can also contact Columbia Basin Research at web@cbr.washington.edu. Best of luck in your analyses, and thank you.